Let's continue. So yes, it's me again. I've got another interesting topic for this afternoon. So I spoke a bit about open source technologies we used over the last 15 years trying to improve things for the industry. And I have to admit that the concept of open hardware is a great addition to that, because we chose open source for our customers because they have long cycles for their products. So having open source hardware in addition, it's really a perfect match. So you can see we achieved a lot within the last 15 years on the open source area. But you know, new times bring new requirements, and therefore we have new challenges. And therefore I want to put a spotlight on some newer technologies. So especially I would like to talk about the Jailhouse hypervisor this afternoon. It is a completely open source based hypervisor, GPLv2, for connected and basically any other things you could probably use. So let's quickly have a look what I want to speak about. So basically, I want to give a quick introduction why we want to use hypervisors, or in which use cases they might be quite useful. I want to give an overview about the Jailhouse hypervisor, what you could probably do with it, what's currently supported, what are the drawbacks of Jailhouse, and actually who's developing it. Well, I will also talk a bit about some challenges we still have to face with this technology. So first of all, why should we want to use a hypervisor? So there's many reasons for that. So one of the main reasons we see for our customers is consolidation. So because if you see how CPUs evolved over the past years, they got more and more powerful, you get more and more cores. So you need some idea how to really make use of all these computing power. So over many years, we had in many machine controllers the concept of different microcontrollers doing different things, which is quite expensive. You just have different controllers. You need to develop these controllers. You need to maintain them. It's pretty error prone. So why not just, if we have this computing power, trying to move things back to one CPU? So this is where a hypervisor can jump in and help us with the consolidation. Another issue we can solve with a hypervisor is isolation of components, which means this can jump in when we talk about safety critical systems. So we want to isolate critical parts from non-critical parts. So we basically call this use case mixed criticality. So this is also kind of a consolidation issue. Just think about if it might be possible to run critical and non-critical things on one multi-core CPU just by having a very clean and deterministic isolation on that. So these are basically the use cases we are thinking about, and also our customers are thinking about, and that's why we are looking into hypervisor technologies. So what do we need to do to reach these goals? Well, if we talk about consolidation, we're talking about computing power. So this means if we choose a hypervisor technology, we want something that scales pretty well. It needs to run on a simple computer if you just want to use it for isolation. If you want to centralize computing power, it even needs to run on very big machines and maybe even server machines. So it needs to basically scale, ideally as good as the Linux kernel does, from a single or dual core computer up to a big 1000 core machine. If we think about mixed critical systems, if we think about certification, what we want to have for a hypervisor is a small code base. Because as bigger the code base, as worse the chances to get a certification on that. So we want to have something very simple, which could probably also pass a certification process. And so once again, if you want to pass certification, you need also not just isolation, you need the best possible isolation you probably could get from a CPU platform. So this is basically where we want to go and where we wanted to have a solution for. And other people also wanted to have a solution for. So now we already talked about containers quickly. So why not just using containers for that purpose? Just dropping different things in different containers. Well, might be nice for deployment, but think about the requirements I told so far. So apart from some strange things about containers we've heard this morning, there's other issues you have when you think about the isolation. Just have a look at this picture. So on the right side, you see the container example. What you need to be aware of when you're using a container, it's at the end of the day, one operating system kernel. And basically the containers are just, well, isolated by the scheduler. So on the Linux side, you're just putting things in a C group and a namespace, that's it. But it's the same Linux kernel underneath all the components. So it's definitely not the best possible isolation you could get. The other problem is, if you think about the consolidation and the certification, one use case might also be you have one single hardware, but you want to run several different operating systems on that. Maybe Linux and some certified, very trivial real-time operating system, like FreeRTOS or something like that. This is basically not matched by the container use case. So if you want to use different operating systems, we definitely need to go with the hypervisor. So this is basically why we need them. The other issue is, if we think once more about the isolation, we need to think about the impact if something goes wrong on the container side. So basically, if you see here, if the operating system gets into a fault, basically all containers are gone, because they are all relying on the same operating system kernel. Even if one of the containers is behaving bad, this might get an influence to the other containers, to the other guests on the system. So we don't have this optimal isolation of the components, which we definitely need for mixed criticality and a lot of industrial use cases. So this is basically why we want to stick with hypervisor technology. So there's many more use cases you could think about for a hypervisor. So once more, you have these consolidation examples. You want to put different controller functionalities on one CPU. You can also think really big on the hypervisor, like when you think about consolidation, it can also mean if you have quite a bunch of different machines running several controllers, it also might get of interest to get more of the logic out of several machines and have it on one single machine, just like in this example. The big advantage you have, you can scale the computing power and the energy for that pretty well. You just deliver the computing power when you really need it, just instead of having the computing power in every different machine. Also a use case where hypervisor technologies can jump in. I will quickly talk about the project we've had with the ISW, the university in Stuttgart, where we thought about these use cases of consolidating things from different machines like into a big server machine. So this is actually also something where we used hypervisor technologies. Or you even could consolidate the computing power of several plants of your company in one big system. So now, which technologies are around? For sure, there are several manufacturers of hypervisor technologies on the market. But, well, we had a reason why we chose Linux for our customers. It's open source, it's freely available, it's available for quite a long time, so it's not bound to a specific manufacturer. So if you want to use a hypervisor, basically we have the same goals. And luckily, quite a bunch of people had the same idea. And there were some people who came up with the Jailhouse idea. This was not our idea. Jailhouse was actually started by a small company, which is called Siemens. This is basically still developed and maintained by Siemens Corporate Technologies in Munich. And this was basically one of their first projects, own developed projects. They made open source and GPL-v2, which is basically a big decision for a company like Siemens. So it's freely available if you want to check it out. It's on GitHub. They have several, they have many different examples, ready to run examples. And it's actually that interesting that other people already started to jump in. Like initially they just supported x86. Now ARM sponsored the ARM 32-bit port. Huawei sponsored the ARM 64-bit port. They have AMD support, which got sponsored by AMD. So there's many big companies interested in this open source hypervisor technology. So the only thing you need to run Jailhouse, this is a basic design idea of Jailhouse, it's using virtualization for the separation of the guest operating systems. This means if you want to run the Jailhouse hypervisor, you need a CPU which is supporting virtualization, which is the case for x86. It's also running on ARM v7 if it has the VT extensions, and for sure it's running on ARM v8, which already has virtualization in the design. So this is a quick overview how Jailhouse is basically working. And they came up with a very, very clever concept. To keep the code base pretty small, they decided not to implement all the boot and configuration code and everything you need from scratch. So what these guys are doing, they decided to reuse Linux. So they boot Linux on your machine, and then they load the hypervisor using the Linux driver infrastructure, and then the hypervisor takes control. This is basically what you can see on this site. So you have one Linux system, we call that the so-called root cell. This root cell will ever stay there. This is basically the management and the controlling instance and monitoring instance for the hypervisor. But it is a fully operatable Linux system. And from the point where the hypervisor takes control, then you could start separate things, like you could isolate cores. And this is important to know. Jailhouse doesn't do any emulation. It just can physically do a physical partitioning of your system. So it can assign physical CPU cores, physical memory, and any peripherals you really have to a guest operating system, or even to a bare metal application. So you can run bare metal on several parts on the system, and you can even run other operating systems. And they are basically separated by hardware. So you have a very strong isolation between these components. Which means even if this one is crashing, the other components will still keep running, because they are completely independent, they are completely separated from the rest of the system. But this only works if you have this hardware physically available. Once more, this doesn't do any emulation. At the end of the day, and this is an important information, with this reuse of Linux, they really ended up with a very small code base, which means for each supported CPU architecture, it's like 8,000 lines of code, which means it is basically possible for a certification. And actually, we really wanted to know if a certification for mixed criticality would work. So we came up with a concept, and we talked to TÜV Rheinland about that concept. And they basically approved that the certification with this concept and this hypervisor would be possible. So it should be possible to go into safety critical applications with that. So we got a clear statement that from the certification authority itself. So this is basically really, really interesting. So I will just jump over that. This shows quickly the configuration of Jailhouse. I told you it scales pretty well. If you Google for that one, this is a project we did with the ISW at the University of Stuttgart. This was basically a project that we wanted to move machine controlling performance into the cloud. So we used the Jailhouse hypervisor for that. It also worked pretty well. Just have a look at the Picasso project from the University of Stuttgart. One thing I wanted to mention at the end of the day, you might ask if there is any performance overhead to the guest operating system. So there was already the question of the latency of preempt RT on ARM CPUs. This is basically what you could see right here on this slide. This is preempt RT on a native ARM 64-bit CPU. So the worst case latency right here was 23 microseconds. So this is basically what I told you this morning. If you put the same system inside the hypervisor, so the real-time system is running as a guest operating system inside the hypervisor, the only impact we can see is the worst case drops down from 23 to 26 microseconds, which is basically caused by the virtualization function of the hardware. But it's just 3 microseconds overhead from the native interrupt coming to the guest operating system in the hypervisor. I think that's actually quite impressive. The numbers look pretty much the same on x86. So I'm running out of time, but 2 things to mention. You need to be careful about one thing, actually. Well, a hypervisor can do proper isolation, but please be aware that not every hardware platform allows partitioning of everything. Just be aware that, like, for example, you need to share the caches on several CPU cores on several platforms. So still one guest can have an influence on the other guest by memory access. And then, this is pretty important, just by isolating the components, well, this doesn't solve your security issues. Just by isolating them, this is a misunderstanding we see over and over again. For sure, all the operating systems running inside your hypervisor, they need a proper security concept and they need maintenance. And just to, you might recall some buzzwords you heard this year, like they were called meltdown inspector. So we got virtualization support in CPUs. Now we even got hacking support in CPUs. So, well, hardware manufacturers have been pretty nice right here. But you need to be aware that with Meltdown Inspector, it is possible to exploit the host by the guest. So you need the proper fixes and patches applied also to the guest operating system. So the hypervisor is not everything. It can help you, but you need a proper concept at the end of the day. So, quick conclusion. Hypervisor technologies can be used for consolidation and separation. There are open source solutions for that. Jailhouse is a perfect match because it scales pretty well. It's open source, so it's freely available. It's GPL v2, and the mixed criticality is basically possible. And we have a clear statement of the TÜV Rheinland that we can do that and we can follow that thing. So, thank you.
One quick question, if any. Again, asking about hardware, do you see any manufacturer arranging for compatibility of cell architecture?
What?
Cell, to be more cell-friendly architecture? Like the separation of caches, for example?
Well, the question is if hardware manufacturers are looking into hardware support for separating things even more, right? Yes, hardware manufacturers are looking into that. There's not much available right now, but what we can see that for the new x86 CPUs coming out, they reintroduce something like cache partitioning, so you could even partition the caches and assign several cache ranges to the guests. So yes, this is something that chip manufacturers are looking into.